Okay, so if you'll recall, our next example was pretty much very similar to 3.4.1. Only difference was they gave us an acceleration instead of a force. Okay, so example 3.4.2 says, Nobel and Mayhem are wearing inline skates. Nobel has a mass of 62 kilograms and pushes on Mayhem, whose mass is 34 kilograms. Mayhem accelerates at 1.2 meters per second squared left. Assume that no friction acts on either person. A says state the reaction and action forces. B says draw the free body diagram of each skater. C says determine the force that Nobel exerts on Mayhem. And D says determine Nobel's acceleration and what assumptions have you made. Okay, so again, let's start by drawing the free body diagram of each of our objects. Okay, now you have to think about both of our objects here and that it says Mayhem accelerates to the left. So because of that, we have to assume that Mayhem is going to be located to the left of Nobel if these forces are exerting on each other, and Mayhem moves in that left direction. Okay, so Mayhem's mass was 54 kilograms, and we're going to put him located to the left of Nobel, whose mass was 62 kilograms. Okay, so again, I'm going to do A and B all in one here. We're going to do the free body diagram as well as state the action-reaction forces present. Okay, so with both objects, again, we know that there's going to be a force of gravity that's pulling them down towards the Earth. And we know because they are on some surface, there is going to be a perpendicular force that is going to be equal and opposite to this force of gravity, that is the force of normal, that is going to cancel out the force of gravity. Okay? And we know this is true for both objects because we're not moving or accelerating in that direction. Okay? So we know that force of gravity and that force of normal are equal. Now, we know that Mayhem is experiencing acceleration in this direction of 1.2 meters per second squared left. Okay, so because of that, we know that there is some applied force that is going to have to act on Mayhem in the same direction of that acceleration. Okay, so there's some applied force that is being exerted on Mayhem in this direction. We don't know what that is yet. What we do know, though, is that this force right here is the action force provided by Nobel. Right? Nobel pushes on Mayhem, and it tells us that right here. Nobel pushes on Mayhem. So because of that, we know this is that action force. Nobel is exerting that applied force onto Mayhem, so that is the action force in this situation. Now, using Newton's third law, what we know is that there's going to be some force that is equal in magnitude and opposite in direction that is going to be applied back onto Nobel. This is the reaction force. Okay, so remember, Nobel exerts the force onto Mayhem, that is the action force. then Newton's third law says there's going to be a force equal and opposite in magnitude, the reaction force that is going to act to the right, and that is provided basically from Mehem pushing back onto Nobel. Okay, so we've gone and done A and B. Let's go and do C, which says determine the force that Nobel exerts on Mehem. Okay, well, if we're looking at Mehem as the object, the only force that contributes to the net force acting on Mehem is that applied force from Nobel, right? That action force of Nobel pushing on Mehem is what provides the net force acting on Mehem. Okay, so the other thing that we know is that any F net equals a mass times an acceleration. So because our F net is equal to FA, and because F net equals MA, then we can say that the applied force in this situation is just going to equal Mehem's mass times the acceleration that he experiences. Okay, so Mehem's mass was 54 kilograms, and the acceleration that he experiences is 1.2 meters per second squared left. Okay, and if you recall, we get a magnitude of 64.8 newtons. And remember, that force is going to be in the same direction as that acceleration. So, the force that Nobel exerts on Mehem, if we go to our significant figures of 2, is 65 newtons in the left direction. Okay. And then part D says, determine Nobel's acceleration. So now we're going to look at Nobel as the object. Okay. And if we think about the net force acting on Nobel, the net force acting on Nobel is going to be, again, that applied force, but is that reaction of that applied force. But what you have to remember is that reaction is going to be equal in magnitude to what we just determined. So it's going to be equal to 64.8 newtons. But instead of going in the left direction, it's going in the right. So this right here answers that part of the question that says, what assumptions have you made? Well, our assumption is again right here, that with no friction, that Newton's third law is holding true. And we get the reaction force that is equal in magnitude and opposite in direction to the applied force exerted on Mehem. And that really is the assumption that we've made in order to answer what is Nobel's acceleration. Okay, now if we look at Nobel and we know that the net force is equal to this 64.8 newtons that we solved for, remember, any net force is also equal to a mass times an acceleration. So Nobel's acceleration, much like we solved in the last problem, is going to be her net force, or that applied force from the reaction, divided by her mass. Okay, so we get 64.8 newtons right, divided by her mass, which is 62 kilograms. Okay, and that comes out to 1.045 meters per second squared. And remember that direction carries forward. The direction of that acceleration is going to be in the same direction of the net force acting on that object. So when we go to our significant figures, Nobel's acceleration is going to be 1.0 meters per second squared in the right direction. Okay, this is Wanny signing off, and may the force be with you.